that will be our Y max. Right down here, this region will be our Y what minimum. Right. So by looking at how the structure has been deformed, so we know that this is compression, this is tensile, right? So we know, so if we look at the cross-sectional view, this will be compression, the top will be compression, the tail will be what? Will be tensile. Okay. So if we were to sketch the normal stress distribution, so over here, right? So on the right hand side, all these are tensile. On the left hand side, okay, all will be compression. So this will be tensile. So M Z over I Z Z multiplied by Y. Then over here will be your minus MZ over I Z Z multiplied by Y. So if you look at the stress distribution, this is how it's going to look like. Okay. Again, this is a sketch. Right. We will come to here, go to 0. Okay. So this is how your stress will distribute. Okay. Now, next you have to draw the arrows. Now, how to draw this arrow? The y-axis, okay, is so-called the material, okay, or material phase, right? Compression means the arrows will be pushing towards the face. Okay, compression. So what do I mean? Okay, what do I mean, Eugene? Now I'm really lost now. Okay, so now if we're going to view this in the X, Y, and rotation about Z, okay, this is the entire beam, right? This is the entire beam. And then this is the wait. This is the centroid. Yeah, so this is our centroid. So what we are saying is that at the top part, right? You follow, I will see how much I can zoom in, okay? And then it's going to be compression, pushing into the what? Into the workpiece, okay? And at the bottom end, right? At the bottom end is pulling away, okay? So this is pulling away, right? So at the bottom end, you can reflect it over the other side. It's pulling away from the what? From this surface over here. Why? Because compression is pushing in, right? Tension is pulling out. Okay, so you can see where the yellow line is, right? This thing is pulling outwards. Okay, whereas on the compressive side, the pink arrows, they are what? They are pushing into the what? They're pushing into the material. Okay, so that's how you draw the stress distribution. Now, it's very different in the context that when it's under, so what we are calculating down here is the stress distribution. Okay, we used to apply a formula where we have what? Stress X is equal to P over A, right? So this formula over here is only for what? Axial loading. Right? This is a standard formula where stress is force divided by area. It's only good for what? Axial loading. But what we are calculating down here is the average stress. Okay, is average stress. Now, what we are calculating now for bending moment is not the average stress. What we are calculating is the what? Is the distribution. That's what I want your to know. Okay, we are calculating the what? A distribution and not the what? Not the average. Okay, are we clear? Okay, anyone, any questions so far, please? Anyone? No? Okay. So the next thing I want to highlight, I think is important to know, okay, before we do like bending moment calculation, we have to know about why are we analyzing structures at a certain point. Okay, like what I told you earlier, we usually analyze structure where it's going to break. Okay, you don't calculate stresses where the structure is least likely to what? Is least likely to break. Okay, now so now we are going to look at the similar characteristic. Okay, let me see how much space I have now. We are going to look at the similar characteristic between simply supported and cantilever beams. Okay. So I want us to look at two configuration. Okay, two configuration of our structure, and there are similarities. Okay, so what does it? So if we look at simply so I'm going to draw simply supported. Now before I go on, why am I doing this? Because when we have a simply supported beam, okay, we can also analyze it like a cantilever beam. I repeat again, if you have a simply supported beam, right, you can also analyze like a cantilever beam. So I'm going to show you mathematically why this is true. Okay, mathematically why this is true. Okay, so if we look at a simply supported beam, okay, like what we had before, so we have a simply supported beam. Again, point A. Okay, so this is our point A. This is our point B. And this is a point C. We have a load coming down here, which is P. The distance from here to here is L02. Right? Now, this is equivalent right? So this on the next one I'm going to draw is a cantilever beam. So for a cantilever beam to be similar to a simply supported beam, so what must I draw? Okay, so this is half of the beam now, right? So this will be our cantilever beam, okay, and this will be our point, or this will be our not our point A, but this will be our support over here. We have a force that's P over 2, and the distance from here to here is L/2. Okay, so this will be our point A, and over here there will be our point B, right? So we already know that failure will occur at point where? At point B. Can anyone tell me, for the cantilever beam, where is it going to fail? Anyone, please? For the cantilever beam, where are we likely to fail? I can use Lux 729 answer. Okay, it will also fail at point where? At point B. Right, failure will occur also at point B. So you can see some similarities already. Yes or no? Okay, so we know that for both of them, structure will fail at point B. While cantilever beam, okay, also the structure will fail at point B. Okay, so now if we were to draw, okay, we were to formulate, okay, the shear force equation. Okay, so what we are going to do is we're going to formulate. Okay, so we're going to formulate. So how are we going to prove that these two are the same? Is we're going to formulate the shear force and bending moment equation. Okay, so we're going to formulate the shear force and bending moment equations. Okay, for both of them. Okay, so we are going to do 0 x to L02. So these are our limits. Okay, so this is between points A to point B. Okay, so probably you guys have done this in 2P before. Okay, so if you formulate them, okay, so what do I mean by shear force equation? Okay, so we're going to analyze from left to right. We know for the simply supported, this is our P/2. We have a variable over here known as X. Okay, and then we're going to assume positive shear and positive bending moment. Okay, so this direction, because we assume positive shear and positive bending moment. So you guys might have forgotten, okay, those direction because of the assumption that we make. So if we analyze from left to right, okay, so this is our analysis direction. Which is from left to right. Okay, so positive shear, the Bx should be coming down, and Mx should be in the anti-clockwise direction. Okay, so when we do static analysis, okay, now we are going to carry out static analysis. Okay, so positive is going up, right? So we have P/2 minus V as a function of X. The whole thing is equal to 0. V as a function of X is P/2 in the limits from 0x to L/2. Okay, then we're going to take moment. Shall mention about moment in the Z direction, variable X. So where we are taking our moment is we are taking our moment from here. Okay, where I just drew the dot. Okay, so the P/2, the force is going to generate a clockwise, so it's minus px over 2 plus by moment as a function of x is equal to 0. So m as a function of x is equal to px